Today, December 18th, 2025, NASA officially confirmed the rumors about the latest interstellar visitor to the solar system, the object known as 3I Atlas. The most important point isn't that it passes like a gravitational bullet, but that it's being propelled. 3I Atlas has an unusual acceleration, not due to gravity, causing it to consistently arrive early compared to orbital predictions from various observatories. When modeling orbits, astronomers start with gravity. The sun dominates, planets create disturbances. But with 3I Atlas, even after adding up all standard disturbances, there's still a margin of error. NASA announced how this acceleration is described in terms of two vector components: a radial component of approximately 135 kilometers per day squared, and a tangential component of approximately 60 kilometers per day squared. The radial component is along the line connecting to the sun. A positive value means there's a force pushing the object away from the sun. The tangential force is the lateral thrust, bending the trajectory and altering the velocity in ways difficult to explain simply as sunlight heating up and gas being ejected straight backward. It's the large tangential component that's intriguing, as it implies geometry. The jets are angled, related to rotation and thermal lag. And the practical consequence is clear. With a small but sustained force, after a few weeks the predicted position can shift by thousands of kilometers, meaning the telescope, even when pointed precisely by software, can still look into a void. Therefore, from now on, observation schedules must chase this drift. The problem is, such a strong thrust would usually be accompanied by a bright dust coma and a spectacular tail. But 3I Atlas is rather faint. The force is visible in its orbit, while the visual cue is subtle. This phase discrepancy forced scientists to examine every other possibility: positional measurement errors, time errors, hidden gravitational forces, radiation pressure. But independent checks, data reprocessing, orbit matching using multiple software programs, and gravitational models of the planets still failed to eliminate the error. The remaining conclusion: 3I Atlas is indeed generating its own thrust, like a natural gas engine. Immediately, the observation campaign shifted to mechanism hunting mode, measuring rotational phases to see the coma's cyclical on-off cycles, taking multi-wavelength photographs to correlate acceleration increases with changes in chemical signatures, and utilizing different perspectives from extraterrestrial assets to deconstruct the jet geometry. The focus was on transforming mathematical matching acceleration into a physical model. If the jet is stable, acceleration will repeat with the same rotational phase. If it is erratic, the acceleration vector will wander, and the orbit will have to be constantly updated nightly. But the biggest question is, what fuel can boost performance while remaining dim? The answer comes from spectroscopy, reading the barcode of light. Data from VLT and JWST reveal that the chemistry of 3I Atlas is unusual. A shock is the presence of nickel vapor when the object is still about 3.8 astronomical units from the sun, a cold environment. Nickel is a heavy metal, so its presence in gaseous form suggests a photochemical mechanism. Light can break down complex nickel-containing molecules, releasing nickel without the need for furnace temperatures. Furthermore, the nickel in the vapor phase appears to be stronger than iron, contrary to the intuition of solar system matter, further reinforcing the idea that this object has a different chemical formula. Meanwhile, JWST focuses on the volatiles and provides a striking figure. The ratio of CO2 to water is approximately 8:1. This is almost the opposite of many familiar comets that are rich in water. And this is key to the bright but dim paradox. CO2 and CO can escape efficiently, but produce little brightness in optical images, especially if the dust isn't abundant. In other words, 3I Atlas could be a gas-rich, dust-poor comet, ghostly in appearance, but with real thrust. Radio observations also show hydroxyl radicals, traces of water being broken down by ultraviolet radiation, proving that water is still present, just not the dominant component. When chemistry meets mechanics, the most plausible model is asymmetrical gas escape through a few concentrated nozzles. Only a very small portion of the active surface, perhaps less than 1%, is needed to create a well-directed jet, producing both radial and tangential components. This also explains why the coma doesn't explode. If the entire surface sublimated, the coma would be enormous and dusty. But if only a few points of jets are primarily clear gas, the object is both powerful and unobtrusive. The role of rotation is also crucial. A rotation period of approximately 16.16 hours is long enough to create day-night contrast and thermal lag, deflecting the jet from its midday position and generating relatively consistent lateral thrust. From here, the story takes on another layer of time. Strong thrust means the object is losing significant mass. Estimates suggest it may lose about a tenth of its mass in about a month, although the exact figure depends on the actual size and density of the core, which still has a large range, from a few hundred meters to several kilometers, depending on assumptions. But whatever the case, the general implication is clear. This intense activity is unlikely to last, so it probably only flared up when 3I Atlas entered the warmer regions of the solar system, after a prolonged, extremely cold interstellar journey. Dynamically, its speed of about 130,000 miles per hour in hyperbolic orbit suggests it is not bound by the sun. It will fly past and then leave, not return. Therefore, it's like a chemical time capsule preserved between the stars, and the spectrum is how we read the label. The most important observation window is right before our eyes. 3I Atlas is expected to make its closest approach to Earth on December 19th, about 270 million kilometers. Not dangerous, but extremely valuable for fine-tuning its orbit, tracking changing acceleration, and finding further spectral signatures. The coordinated efforts of Hubble, JWST, and the Large Ground Telescope aim to connect three things: coma morphology, gas chemistry, and acceleration vectors. Acceleration can be non-constant. If it drops sharply, a main nozzle may be running out of fuel. If it surges, a new crack may have opened. By tracking these breaths, astronomers can map the activity of an unsolved bright spot. And even after December 19th, if brightness remains sufficient, the object could be tracked in depth into 2026 to observe the shutdown process. Which gas stops first, whether the metal weakens, and whether acceleration is lost or redirected. More broadly, next-generation surveys like Vera C. Rubin are expected to detect more interstellar visitors, and 3I Atlas could become the opening lesson on the signs to look for. Early activation, a rich CO2/CO spectrum, strange metallic lines like nickel, a faint coma with non-gravitational acceleration, and a measurable thrust vector. In short, NASA has stamped a conclusion that is both simple and startling. 3I Atlas is being propelled by a natural engine powered by the operating gas, powerful enough to change its trajectory while maintaining a discrete appearance. And that's what makes this encounter so special. We're seeing the physics and chemistry of another world unfold in real time.